Okay, so I don't know if that was your break or not, Will. But I did want to say, as I mentioned, where we left off is there has been now people conducting detailed kinetics in the condensed phase. It's really some important new work in this type of chemistry. And this shows some examples of showing what new types of channels have been found. So what I just mentioned before, if I have this HONO elimination, what was proposed before is I'd lose one HONO, eliminate, and then I'd start wrapping it around the chain. I'd lose a second HONO, and then I'd lose a third HONO, and what I'd end up with is molecule on the right and the top right referred to as triazine. So the ring did not open. Okay, but from these new calculations and the later results, it says once you basically lose the first HONO molecule, the ring starts to weaken. And so you can follow path 1A then. That shows after I lose this HONO, now the ring opens and I get this structure and it starts unzipping then, much faster. And now this looks like it's the favored route versus the one on the top, if it involves HONO. And HONO, again, would be a lower temperature process, which highly would occur then in the condensed phase where temperatures are lower. Okay, the bottom process P2 here is basically the NO2 bond scission, and then the breaking of the ring, one bond removed, so you can see I lose the NO2. This was shown before. The next weak bond is this one, and the next weak bond is this one, and the ring opens up. Okay, and I can form different channels here. Okay, and the study went on to basically look at other possibilities of what type of reactions could be occurring. The one I refer to here is P3. This is a reaction with NO, and what you're finding then is you can have either a displacement reaction or an abstraction reaction, where now with the RDX, the NO comes down, and it can displace this NO2 group and just have the NO and NO2 go away. Or the NO could come down and try to abstract one of the O atoms to form the NO, and I'm left with an NO2. And then somewhat structurally, then it shows that would proceed by, again, going down this route here. Another example is to go through basically prompt oxidation with HONO and ONO2. It's a different sort of route that I showed before. And then the third route here is hydrogen abstraction via NO2. So these are sort of secondary reactions where I've started to form some of the secondary products. The NO2 comes back to the original RDX and starts abstraction reactions. Okay? And so condensed phase models were built, and here's an example of trying to compare it to experiments. So again, this is a very slow heating rate experiment. Well, no, he did this both, sorry, in his rapid thermolysis experiment as well as a low heating experiment. But the results here are for the rapid. So here he's looking at confined rapid thermolysis, FTIR spectroscopy, where he put like half a milligram of RDX and it's heated at 2,000 Kelvin per second to 548 Kelvin at 1 atmosphere. And the experiments that he monitored with the FTIR as a function of time, it shows this evolution of species that I show you in the bottom, and his model predictions are on the right. So again, you know, they're not perfect, but they qualitatively show the same species being formed, the right type of time scale, and some of the same sort of characteristics. And what they concluded then, HONO illumination at these temperatures is more important than the NN bond scission in the liquid phase, and HONO elimination is followed by ring opening right away instead of that consecutive HONO formation. Okay, and if I look at basically just like the double base propellant, this is a schematic of what the RDX flame might look like above an RDX crystal. It has the same sort of characteristics. And you know, how do people put these models together? You know, do they just dream up, you know, it has a fizz zone and things like that? Well, what they do is they try to look at experiments. So this experiment over here of RDX burning, they look at the surface and they see, well, in the surface here, something's happening. And that's actually, if they study it in films, they can actually see bubbles form, and it looks like a fizz zone. And so, okay, well, if I'm burning RDX, then phenomenologically, I've got to include some sort of fizz zone in my model. And so that's how they start developing what this structure should look like. And so you can see, just like in the double base, I go through a thermal wave in the solid, I heat it up. I can have a phase change of the crystal, going from one phase to another. Then I go into basically this sort of zone where I'm starting to form a mixture of gas and solid, and then I get into a fizz zone, which is mainly gas, and maybe little droplets are coming off the surface. And then I go in my first stage, my dark zone, and my second stage reaction. Okay, so it has the same sort of characteristics. And again, as I told you, this is a consequence in the gas phase of having NO2 as your oxidizer and forming NO. Some comments about the type of models that have been formed there. Numerical models have included detailed chemical kinetics and transport phenomena in the gas phase and thermal decomposition of subsequent reactions in the condensed phase. This modeling work that I'm showing you here was done before Tynell's work of the detailed condensed phase. Formation of gas bubbles in the subsurface layer to molecular degradation and evaporation has also been included. So at the surface, the RDX can vaporize as much as decompose in the condensed phase. And so what is more important? Is it the evaporation of RDX, and in the gas phase I have RDX molecules, or how much condensed phase decomposition I have and I don't get any RDX in the gas phase? The model I show you here is probably one of the more detailed models that have all this physical structure. It was done by Lo and Yang. And just again to show you some of their results, it does a pretty good job of predicting the burning rate as a function of pressure, particularly in the lower pressure regime. I showed you this sort of deviation slightly around the 20 megapascal region where I get a higher burning rate experimentally. These are the sort of temperature profiles that were predicted at different pressures, so going from 1 atmosphere, 5 atmospheres, 20 to 90 atmospheres. You can see this thickness of the thermal wave in the condensed phase here, how it changes with pressure. Okay, so the higher pressures have this very narrow thermal wave. At low pressures, the thermal wave propagates deep into the surface. And you can see the gradient at the surface is getting steeper and steeper with the temperature profile getting closer, so it's accelerating the reaction rate. One thing you're not seeing here is that dark zone region. Okay, it's not showing up in these calculations. Comparison of species predictions with experiments that were performed by doing either microprobe analysis above the surface, or doing mass spectrometric measurements, or doing some PLIF measurements. Of what you see, again, coming off of the surface, this is HCN. Some of it's formed, goes away. You form NO, it goes away, and then as the NO goes away, you form N2, and you're left with, remember, RDX is nearly stoichiometrically forming just CO and H2O and N2 in the final products. And you can see then the experimental results on the right. So, you know, they're good, they're not perfect, and you can understand why because of the structure of the surface, and this is a very transient dynamic process going on. They've measured different other things out of the modeling and experimentally. In this plot, they're looking at how thick is the molten layer. So this is also related to how much time I have for condensed phase reactions. Because if the molten layer gets thinner and thinner, I potentially might not have as much time for condensed phase reactions, and maybe evaporation becomes more important. Okay, so again, this is a function of pressure, and you can see that the thickness of the molten layer gets thinner and thinner. And again, that's if I showed you before, that thermal wave was getting thinner and thinner as I went to higher pressures. On the right-hand side, predictions of the surface temperature. So again, the surface temperature's going up with pressure. So if I had a channel, remember I showed you that there was two different types of channels. That one had a low activation energy forming formaldehyde and N2O, and the other one had a high activation energy that went to NO2 or HONO and HCN. Well, as I go to higher pressures, the surface temperature is going to get hotter. It's start going to favor the NO2 route versus the N2O route. Okay, and the other thing that's shown here is basically the surface void fraction. basically how much gas versus condensed phase material is near the surface as I go. And you can see that sort of decreases as I go up in pressure. The last thing I show here is, calculating burning rates is relatively simple because it depends most importantly on your prediction of temperature. Same thing in a gas phase hydrocarbon flame. If I get the temperature profile right, I'm going to get the laminar flame speed right. It's not going to tell me too much about the detailed chemistry. We find the same thing in burning rates of solids and liquids. Okay? But going to the next level of comparison is, can I get the temperature sensitivity of the burning rate right? So remember what the temperature sensitivity of the burning rate is. This is if I change the initial temperature of the material, how much does it change the burning rate? Okay? So it's another important metric. And you can see here that in this particular case, modeling of pure HMX, RDX, AP, and generally the symbols are the data that show, in the case of HMX and RDX, the temperature sensitivity goes down with an increasing pressure. In the case of AP, it went down and came back up. Crudely, it's getting close to that type of behavior, but more improvement definitely needs to be made on being able to predict the temperature sensitivity. Okay, since we don't have much time, and we need to make sure we're out there for the camera, let's not take another break because I want to kind of move on to some of these other notes. I thought I had something else here, sorry. I'll show you tomorrow. I had some movies of burning rates, but I don't see them here right now. Okay, so, I've talked about the oxidizers, a little bit about binders. I now want to talk about composite materials and models for them and how they burn. Okay? So if I look at a typical solid composite propellant mixture, and this based on ammonia perchlorate, this is what I might have. Where you can see the 12% of the binder by weight is HTPB. The total solids loading is 88%, 70% of its oxidizer, and 18% of its aluminum. If I look at this, the oxidizer, I have different, basically, distributions of diameter sizes that I need to mix into this system, and that's for several reasons. One, I get a higher packing density, so I can get a higher solids loading if I have different size distribution of the particles. Okay, the second thing is it affects the mechanical behavior too. I get better mechanical strength in the system. So I give you some ideas of the types of size of the oxidizer particles that are used. So the fine oxidizers are like between 1 and 15 micron. So that's like bacteria to talcum powder. Medium oxidizers like 20 to 90 micron, like white blood cells to hair. And the coarse oxidizers are like 200 to 400 micron, which is like fine to medium beach sand. Okay, and the aluminum is on the order of 20 to 50 micron initially. So in this picture here, what you're seeing is a schematic of what it might look like. So here are the coarse particles, the medium and the fine oxidizer, and the blue are basically the aluminum particles. And you can see how this matrix fits together to get a high solids loading. The bottom right here is basically a picture of the coarse AP particles, just by themselves. If I look at the picture on the left, it's showing basically a picture of the composite propellant. And so here's the coarse particles embedded in the binder. And in the binder, you can see basically barely different sizes of AP in the aluminum particles. So again, I want to mention a little bit of what's been done modeling there and showing you that hierarchical structure. Again, the same thing happens here with composite propellants. The idea is basically to start with a simple geometrical system, simple chemical system, and kind of work to more complex systems. So here, first understand one-dimensional monopropellant. So this would be the AP by itself, so as a single ingredient. Model the gas and condensed phase chemistry, and basically compare it against surface regression rates in those models. The next level would be a 1D composite propellant. So add a chemical complexity without spatial complexity, and look at the chemistry interaction. So you might ask, well, how do I do this in a 1D system? Maybe I use a counterflow system, okay, where I have a solid oxidizer particle, and coming from the other side, I have basically the decomposed products from the binder. Okay, and that's what I mentioned here, 1D counterflow. Add diffusion flame, but remain 1D. Chemistry with fluid mechanics. Oxidizer with binder decomposition product chemistry. Next level would be to go to a more complex geometry, say a 2D sandwich, where now it looks like a sandwich where I have a binder, an oxidizer, and a binder in layers. And you can create then multidimensional flames. You can start looking at how the monopropellant flame interacts with what's referred to as a diffusion flame that's involved. Okay, and then go on to 2D realistic packing. So now I'm going to have some sort of packing code that actually creates those matrix of particles. And I look at diffusion flame interactions and the evolving surface geometry. And it basically becomes in a 2D structure first, and then moving on to a 3-dimensional structure. Very complicated calculations. And at the 3D level, doing realistic work would take a long time on a computer. So, why are we interested in these kinetics-based models? Well, two important metrics. The specific impulse is important, and as a consequence, the flame temperature is important. They're easily calculated from thermodynamics, but what we find is the kinetics controls the critical ballistic properties. It controls the burning rate, the pressure exponent, the temperature sensitivity, ignition and transient combustion, combustion instability, cook-off, and deflagration and detonation transition. So if I want to be able to predict those, I've got to understand the chemistry. And I can't just put in, empirical rates for that chemistry. I've got to understand the details, so maybe I can reduce it to make simplified mechanisms. Must know ballistics to design rocket motors. Only 33% error in the burning rate can lead to a 300% overpressure and a catastrophic failure of a system. The pressure exponent is critical to the system design. For example, if I want to have MESA operation for stability or a high exponent for a Pendle throttleability motor. Global models right now are inadequate. They don't uncover the real kinetic mechanisms. They can't predict combustion instability, ignition, DDT, etc. And as a consequence of that, they can't help design new propellants. And really, that's the ultimate goal. Can I start building just through models, basically propellants that I could use then to basically design them? So here, looking at AP propellant properties. AP is an atypical oxidizer, although it's the most widely used. It significantly increases the burning rates relative to pure AP, and there's a significant effect of particle size. Small particles burn faster. They produce an excess of 30% oxygen above the monopropellant flame. And they have a 1.3 hazard classification. The low pressure deflagration limit's 20 atmospheres. And it's basically an exothermic reaction. The biggest problem is that it has chlorine. And there's a lot of research and trying to find an appropriate replacement for AP, but unsuccessful to date. AP is just that good of a oxidizer for solid propellants. And so what I show here on the right is the burning rate as a function of pressure. And if I take AP and look at its pure monopropellant deflagration rate, I get this curve. But if I mix it with a little bit of binder, I can adjust the ratio of the binder to the AP, and now I can get a whole range of burning rates, and those burning rates are faster than just pure AP. Okay? That's not true for the nitramines, such as, say, HMX or ammonium nitramide. Ammonium nitrate. You can see here, if I look at, say, HMX, here's its burning rate by itself. And if I mix it with a hydrocarbon, I get a wider spread on what I can generate, but the burning rates are slower. Why is that? Anybody remember? What's the HMX form in its final products? It forms just CO, water, and nitrogen. It's perfectly tuned in terms of its elemental structure to form the lowest molecular weight with the greatest heat release. So there's not any excess oxygen. So if I mix it with a fuel, I'm diluting the system and I'm slowing down the burning rate. Whereas that's not the case for AP, because remember, it has a positive oxygen balance, and it's supplying that oxygen to the hydrocarbon to get more energy release out of the system. Okay, here's sort of the current understanding of what the structure of an AP composite propellant might look like when it's burning. So here I'm looking at the coarse AP particles. And below the coarse, I have medium and fine. So I'm assuming you don't see them down here, but they're down here. And I'm not including any aluminum right now. Okay, so the AP by itself decomposes exothermically as a monopropellant. And so it creates a flame above the large crystals. Okay, so out of this flame, I've raised the temperature, and I'm forming a lot of molecular oxygen now. Okay, in this region over here, if the particles are small enough, and as I pyrolyze the binder, they start coming off of the surface, and because of the length scales of the small particles, I can get sufficient mixing before complete burning. So it starts looking more like a pre-mixed flame with very fine particles that, as they sort of start to decompose, they mix very quickly with the pyrolysis products. And I get then what looks like a pre-mixed flame that's very fuel-rich. So off of this, I got excess hydrocarbon, but it still burns like a pre-mixed flame. So now I got a lot of a fuel-rich mixture coming off this, a lot of hydrocarbon, and here I got a lot of O2. So as they start to diffuse towards each other, I form a diffusion flame above the surface of the large AP crystals. Okay, so now you've got, it's a very complicated flame structure, and you can start asking yourself, well, what if I start changing the ratio of the large crystals versus the small crystals, the loading, and what happens if I change the pressure? What's going to burn faster now? So it gets to be a very complicated flame structure. Obviously, it's going to be three-dimensional. If I start looking at the dimensions, this distance here is probably no more than 50 micron, if even that. Remember I said this is probably on the order of 200 micron. And so, this is definitely a three-dimensional surface. The flame structure is three-dimensional. What's happening in the condensed phase is three-dimensional in terms of heat release and whether or not there's a melt layer, et cetera. So here's basically some modeling results of just AP decomposition as a function of pressure. So just the pure component, okay? And this is some work that was done by this group, Chen and McQuaid. Basically what they found is if I'm looking at the pure AP, remember it's an ionic compound, so I have NH4, ClO4. What I find is the first step is a proton transfer. The H atom on the NH4 moves over to the perchlorate to form hydrogen perchlorate, and I form ammonia coming off the surface. And you can model that pretty good then. And so they actually predict the low pressure burning rate data. But remember, if you remember from yesterday, I showed AP has a very funny burning rate as they go to higher pressures. And here's their prediction. It goes right through it. It can't predict it. And that's the same of many other slope breaks. And I think I said a little bit about this before. The condensed phase and interface surface phenomena is the least understood. The surface reaction zone is very thin, multi-phase, and has a steep temperature gradient. Several studies use photography to observe the burning surface. Then the sample was quenched and examined using scanning electron microscopy. Other studies use fast thermolysis and FTIR to measure decomposition products. Typically, microthermocouplers are embedded within the propellant sample at various distances from the surface to measure the thermal response of the propellant. And obviously need information on the condensed phase reaction, AP phase changes, and binder decomposition before reaching the surface itself. So here's, I mentioned how these models could be developed in a very simple form. Okay, so this is an example of a counterflow experiment where an AP crystal was taken in the form of a cylinder. It was mounted in a tube, and in this particular case, it was held in position by putting a thin wire over the surface. And then there was a linear position transducer mounted to the bottom. So as this top surface started to be consumed, the linear position transducer pushed it up tight against the wire so its surface position never changed, although it was being consumed. And you can measure the regression rate from the transducer that was below it. And what's flowing in the opposite direction then could be different fuel fragments from the binder. Okay, and so some of these cases are pretty simple. This is with just methane flowing against the AP crystal surface down here. And what you observe right away is look at this different luminosity is an indication of the fact that different species are being formed, and you're seeing chemiluminescence, so the flame structure above the surface from the monopropellant flame. And out at this position, remember, the AP forms a lot of oxygen. So right in here in the center is the diffusion flame between the fuel coming down and the oxygen that's formed from the monopropellant flame above the AP surface. And you can see here, building these simple gas phase models, the models again are doing relatively good with regards to experiment. The symbols on the right-hand side show about 12 scalars between the outlet of the fuel and the top surface of the AP, and the solid lines of the model, and relatively well predictions. Then to increase the complexity, here's one example of what was done to get a 2D gaseous fuel AP flame. That AP crystal was taken and a small hole was drilled through it. Okay, and now the methane is flowed through that small hole. Okay, so now what you're starting to see here experimentally, this region out here, here's the AP pellet, this region's burning, this is the monopropellant flame that's sitting above the AP surface. Okay, and then coming through the center here is methane, and you can see now there's O2 gas coming off at the top of the monopropellant flame. There's methane in that center hole, and you're forming a diffusion flame between the two. And so again, now how well can you model that experiment? It's a pretty well-defined experiment, so can you get the chemistry right in the system? This is starting to show the complexity of what happens when you start changing particle sizes in the system. When I go back to that flame structure, how important is the monopropellant flame off the top of the coarse particles controlling the rate versus that sort of pre-mixed regime controlling the rate? And you can see here that on the right-hand side, for example, this solid line here is the burning rate being controlled by the premix limit with basically using 10 micron particles. Then as I go to higher and higher pressures, basically I start moving into the diffusion flame limit with being the controlling factor. Okay, and if I change the particle size, of the AP and the propellant, it leaves the premix limit being controlling at lower pressures very quickly to the diffusion flame limit at a lower pressure. Okay, the point I want to make here is, again, you can change the particle size to change the behavior of the system. And it just complexes the system, and people use that basically then to modify burning rates. This is kind of what's being done now. A 3D modeling of heterogeneous propellants over the past 2 decades. Parallel computing has become a staple of engineering calculations with multidimensional simulations of heterogeneous propellants following this trend. Jackson and Buckmaster have carried out the first 3D dimensional simulations of solid propellants in 2000. And this was based on a random packing algorithms, which were used to develop the microstructure of heterogeneous propellants and an unsteady solid gas numerical code for the combustion problem. So here you can see basically their packing algorithm. Okay, and what's shown here then again is the different sizes of the AP particles, different sizes. I think this actually has aluminum particles in it as well, potentially, or they have put aluminum particles. The gray spheres have diameters in the range of 5 to 15. The blue spheres have diameters 16 to 42, and the red spheres have diameters of 46 to 211. So in this particular case, they did not, it was just an AP HTBB model. So where you don't see anything is where the binder's located in the model. And then having this model, then as I said, they couple it to a combustion model, and they start predicting the regression rate. Now the combustion model in these calculations is very simple. It basically involves maybe 3 overall steps because they cannot include the detailed kinetics because they would take too long computationally. Okay, and this is an example of showing the steps that try to account for that flame structure I showed you before. Okay, so where they take the AP, it decomposes to form products. Some of the AP can react with the binder to form products, and then those products that the AP initially formed in a diffusion flame can react with the HTBB to form the final products. Okay, so I have those sort of 3 regions: the large diffusion flame, the monopropellant flame, and that sort of pre-mixed flame with the small particles. And the question then is which of these steps dominate at a particular condition? And what you'll typically find is if I go to higher pressures and have coarse particles, that monopropellant flame makes the crystals propagate down into the binder. So you get little wells, okay? But because it's burning so fast, those large crystals, the gas flow is coming very high off of those. And what it does is it lengthens that secondary diffusion flame to be very long. So that diffusion flame, that's the long one and the tall one, really doesn't contribute to the burning rate. The heat release is too far from the surface. Okay, so it's either being controlled by the monopropellant flame above the AP crystal or that pre-mix zone where you have the small particles mixing very quickly with the binder itself. And to sort of make the chemistry simpler, what they often do is they'll homogenize the small particles with the binder, so they don't have to track the small particles. And by doing that, they're just saying, I've got a pre-mixed system. So you can see on the left-hand side is the full pack, and they took a certain range of small particles, and they said, okay, I'm going to homogenize it with the binder and make it into a pure pre-mixed system. And so what they end up calculating then is the pack on the right. And so really now they're looking at fewer particle size distributions. And this is just a 2-dimensional calculation of that, not the 3-dimensional. And you can see here the flame structure that I sort of just talked to you about as a function of pressure. So again, the large AP crystals in red at low pressure of 6.8 atmospheres. This is the interface here. You can see the diffusion flame, the secondary diffusion flame above the large AP crystals. As I increase the pressure, that starts getting further and further away from the surface. And what starts controlling the system then is either the monopropellant flame at the surface or this sort of pre-mixed flame near the surface away from the large crystals. So as the pressure increases, the premixed flames draw closer to the surface, resulting in a faster burning rate, and the standoff distance of the diffusion flame increases, decreasing the flame's contribution to the burning rate and increasing the surface topology. Okay, and I think this is probably the starting the calculations with that 3D pack model. And in this particular case, they did include some aluminum particles that are coming off the surface. So this is really state of the art. And in fact, there is a code that I think is free to download called, I'd have to look it up, it's Fire something, that was built by Tom Jackson, who's now at the University of Florida. And you can basically obtain it from him to do these sort of calculations. But again, there's a lot of work that needs to be done. They're very intensive, and they do a pretty good job of predicting burn rates as a function of pressure, as they should. Okay, so I want to go back, and this is something, I want to go back and just show you some burning rates of different materials here. And I want you to think about physically what's going on, because I've talked about the importance of slope breaks. And so I'm going to show you very quickly a number of traces of burning rate profiles as a function of pressure. So I've already shown you one on the left, JA2. And you can see there's a slope break close to 20 megapascals. If I look at the one on the right, this is a very controlled mixture of AP with HTPB, or RD or HMX with HTPB. Okay, and it's only a mono dispersed size of the crystals. Okay, so it doesn't have multi-size, and I have to worry about the effects of multi-sizes. Note in both cases where the slope break occurs. It's about the same location, right? I come over here to the pressure dependence for ammonium nitrate with addition of a stabilizer. Look where the slope break occurs. About the same pressure. In this case, it's the slope break is decreasing, it's not increasing. So we got interested in that, and I think I showed you this facility before. We built this very high pressure facility to look at what's causing those slope breaks and visually observe them. So this particular system, as I mentioned, we can go up to 50,000 psi with optical windows, take a look what's going on all through that pressure range. And so we said let's look at nitromethane first, because if you remember, nitromethane has a slope break at about 18 megapascals in the same range. Okay, and I kind of showed you this before, where I took the ratio of the burning rate versus the laminar flame speed of the vapor. And if I get to high enough pressure, the laminar flame speed and the burning rate should agree. And so the blue symbols here are the experiments of the liquid. The solid line is what basically condensed phase model would predict, and you can see it doesn't predict the slope break, the black line. If you look at the green line, it's the vapor phase flame speed with an ideal gas. And if I put in a real gas, then you can see the real gas causes the flame speed to increase at the higher pressures. And potentially, eventually, these two are going to merge together. If I just look at the vapor phase flame, what do I know about the flame speed of a hydrocarbon as a function of pressure? Typically decreases in the beginning, right? But if I look at burning rates of propellants and I increase the pressure, they always seem to increase. But here, if you just take the mechanism for nitromethane in the vapor phase and you go to low pressures, what you find is initially it decreases. Then I get to 1 megapascal and it starts to increase. And so these numbers here are sort of the overall reaction order. Okay? And then as I continually increase the pressure, eventually the flame speed increases, and again, it gets to a value of reaction order between 2 and 2.3, and then at very high pressures it comes back to 2. So again, there's a very unusual behavior. Take a look at the thickness of the gas phase flame as I increase the pressure. So if I get to 100 atmospheres, the flame thickness is probably less than 100 microns. Maybe you're getting close to maybe 10 microns or so there, maybe even close to 1. Okay? So the thickness of the flame in nitromethane is getting very, very thin. If you look at the compressibility factor through the flame, the pressure's missing here, but I think this was 100 megapascals. You can see that the compressibility factor is not 1. So through the flame, it's going from like 3.5 down to about 1.4. So indeed, real gas effects are important and can't be neglected. So let's take a look what we visually saw as we increase the pressure here. So what I'm going to go back. Oh, I thought I had it. Here, I'm going to, in terms of this, I'm going to show you a film of the burning rate here, a film of the burning rate here, a film of the burning rate here, and some up here. Okay? And let's see what we learned by just observing the process. Note that if I'm looking at pure nitromethane, the critical pressure is between 7 and 8 megapascals. So the critical pressure is obviously below the transitional pressure we're seeing here, okay, for pure nitromethane. Okay, so let's look at the lowest pressure case first. Okay, so that surface is actually going down. We're using a high-speed camera, but it's moving so slow, you don't really see it. We put an emitting diode inside the chamber so that it would reflect off the surface so you could see where the surface was, and that's what the green is. Okay, so I'm going to go now from 3.5 megapascals. Note that there's no luminosity from the gas phase flame either. I go up to 10 megapascals, which is below the critical pressure for that slope break. And now you can, it's still going down. Important thing to look at is the surface is clearly flat, one-dimensional, but now I'm seeing luminosity. So now something's being formed that's chemiluminescent. It's not soot. Okay? Now I go to 18 megapascals, right where the critical pressure was, just on the low side. Look at if you can clearly look at the surface, you'll see now surface waves are starting to form on the surface, little surface waves. And now and then you see a little bit of a ejection of maybe a droplet or something like that. Okay, so what happens when I get to the critical point? What happens to the surface tension? It goes away, right? And so what you're starting to see here is the waves are being created and I'm losing surface tension. Okay, so now I'm going to go just right above that critical transition point. And now all of a sudden, this is what you see. You see this beginning of a hydrodynamic instability caused at the surface. I've lost the surface tension, and now effectively what I'm doing is I'm increasing the surface area where the burning is taking place. So the burning rate's taking off like crazy. Okay? You know, before I observed these, and nobody observed this before, they couldn't understand, well, what's going on that makes that slope break? I go to a slightly higher pressure. I'm still in that steep transition range where the pressure exponent is about 10. Now you can clearly see the hydrodynamic instability being developed. Here the hydrodynamic instability is going up and down the tube. Remember, the nitromethane is burning inside a tube. And I go to slightly higher pressures. And now you see this stability slightly going back and forth across radially. So again, very large instabilities. Okay, now I'm going to go, the next case I'm going to go is when if you remember, if I got the very high pressures, the slope started to come back to what it looked like at low pressures. But the burning rate was much higher. So look at now, I've lost the hydrodynamic instabilities, but I'm developing a very cellular, turbulent flame front. I increase the pressure again, And notice you don't see a clear distinction between what looks like an interface between the reaction and what's below the reaction. So it's looked like I've got almost one fluid burning, very much like a turbulent flame of a gas phase system. Okay, and the same thing happens as I go up to the highest pressure here. It almost looks like I got a parabolic profile, and if I'm looking at it from one side to another, it's slanted. So what's basically happening is, remember the pure nitromethane had a critical pressure of 7 or 8 megapascals. But under those conditions, the surface was below the critical temperature. So I was in a transcritical regime. As I continued to increase the pressure, I'm getting heat feedback from the reaction above the surface, which is starting to raise the surface temperature, and I'm approaching the critical temperature already. I'm above the critical pressure, and so the system's going supercritical. Okay? And that leads initially to the instabilities. If I get high enough pressure, it just becomes a turbulent flame. Okay, and basically this plot here just summarizes those. Okay? Now, remember, this was done in a tube. So I recognize, well, this is a turbulent flame. I know length scales sort of affect the size of the turbulence scale, right? So if I decrease the length scales, I should expect I'm decreasing the largest eddies, so potentially I'm going to decrease the propagation rate. Okay, so this is just looking at, here's that critical transition pressure, about 18, and this is for a series of different tubes. And what you can see is as I decrease the tube diameter, the propagation rate decreased, so I'm decreasing basically the effects of the turbulent flame. I'm still getting a relatively steep transition, so there's probably still some hydrodynamic instabilities, but the turbulence level is going down, and consequently, the flame speed's going down. So one of the questions is, and I don't know if I show it here. Yeah, I did show it. What we did is we continued to decrease the size of those tubes until the flame quenched. Okay, and the tube diameters get down to, you know, on the order of less than a millimeter in this particular case, and down, it was still burning here in probably a 150 micron tube. Okay, so you can see there's a transition between what looks like a slope here and a slope here with tube diameter. This transition we think is heat loss because the tube sizes are so large. And as an estimate, what you could do is you could predict then, if I just extended this and extrapolated to 0, you might be able to get what would be representative of a propagation speed where you minimize the turbulence level. Okay? And we obtained that, and then we compared it back with those real gas calculations. On the right-hand side, you can see how the quenching diameter changes with pressure as well. Okay, and so what I'm showing here is what we assume now is the effect of just the supercritical real gas effects without turbulence affecting the burning rate. Okay, and you can do the same thing. You know, I mentioned if you remember, we looked at this hydroxyammonium nitrate. And what you do there, that's a solid crystal. You mix it with a solvent water, and you can add a fuel to it like methanol, and you can create another monopropellant. And this was to replace the hydrazine. If you remember what its burning rate curve looked like, it went up quickly, plateau, came down, went up, and it does some very strange characteristics. And so here's what it looks like. We went to even higher pressures. So in the case we're looking at just 13 molar HAN, so there was no methanol, so this is just that hydroxyammonium nitrate dissolved in the water, you get a profile that looks like the orange curves, where it goes up, plateaus, comes down, and starts going back up. If you add some methanol to it, it follows at low pressures the same thing, plateaus, comes down, goes up, and then plateaus, comes down, and goes up again. So what's going on there? What's leading to all these transitions? Okay. The critical pressure for water is like 22 megapascals. The critical pressure for methanol is about 8 megapascals again. And I did forget to mention, you can calculate thermodynamically through mixing models what the critical pressure of a mixture should be. And if you go back to the nitromethane case and you do that, you calculate basically about 16 megapascals, which was very close to the 18. Now that you know, the calculation there, I assumed you're looking at a homogeneous mixture, right? But we know in the case of nitromethane, what's going critical is just probably the interface, because the heat's coming from the gas phase back to the surface. Okay, and as a consequence of that, I got to account for diffusion to and from the surface as well. So you can't just simply do a thermodynamic calculation to predict what the critical conditions would be for a mixture. You've got to actually account for what's at that surface in terms of composition, and that involves the mass diffusion equations as well. Okay. But here, you know, the question again is what's happening. So let me show you in the case of the hand methanol interface, and we're looking at this is the higher pressure regime, 6 megapascals, 14, 50, and 70. So at the lowest pressure here, which is still pretty high, you don't see, this is the interface here. You don't see any luminosity above the surface. If I slightly go to a higher pressure, to 14 megapascals, which is now in that first dip region where it came down, you start to see a luminous flame, and it starts looking turbulent above the surface. I go back up to that plateau regime again. And now I'm starting to see a slanted flame front that looks cellular, and it's harder again now to see. Note that the flame front over here is still flat. Now I'm starting to see the disappearance of that flame front, and it's starting to look a little bit like that nitromethane flame. But what's really interesting is what happens if I go to the highest pressure. It becomes very slow. I've got nearly a flat surface again where I can see a distinct interface, and you can see waves at the surface. So what's going on? In this case, I don't have a good explanation. And you can see that, you know, these propellants are going to become their burning rates are going to become very dependent on knowledge of these critical properties, which is, again, a good area to start looking at in terms of research. I do want to mention, you know, if you look at those AP-based propellants that I showed you where the slope break was, it was about 2,500 psi. And I think I mentioned to you this before, that the highest motors in which an AP composite propellant runs is about 2,000 psi. And the reason is they can't go higher because of that slope break. Okay, so, you know, if I now, and people had been looking at how do I get around that? They were looking at it before by changing particle sizes and doing, you know, physical things to the matrix. But now they got to start thinking about, you know, how do I control thermodynamics and things like that? How do I change the mixture to change critical properties? And so I think it's a good area. It's not well understood. I'll stop there because I want to make sure we got 5 minutes yet. Let me show you one other thing, and then we'll stop. So in that those mixtures of that hand and with the methanol and without it, we took temperature profiles with a fine wire thermocouple as a function of pressure. So this is another interesting phenomenon. If I look at the methanol case on the right, this is the lower pressure case. And if I look at the temperature profile through the wave, here's the initial temperature. It goes up, and here's the temperature behind it. I increase the pressure a little bit. That surface temperature goes up a little, but behind it, some far distance away, is the next stage reaction. Okay, so again, in this system, there's NO being formed, and what I'm seeing in the lower pressures, the NO is not being converted to N2. Okay, but this is a relatively low temperature flame, and so what it's meaning is the condensed phase reaction is controlling the burning rate. The gas phase reaction has no influence. Now I go to the highest pressure I showed you, which had the slowest burning rate. Notice its temperature profile. It goes to the highest temperature right away, but it has the slowest burning rate. So again, what's going on? Is still, obviously I can't resolve right at the surface with these thermocouples, but is it still the condensed phase, even at the highest pressures, that's somehow controlling the burner rate? Okay? These temperatures here are very close to the boiling temperatures, first of methanol, and then of water. So you can imagine when I get to that first dip, the 7 megapascals, when the burning rate goes down initially, potentially maybe the methanol by itself has gone critical. And as a consequence of that, I'm getting less bubbles and less surface area, so the burning rate's going down. And then eventually the water is still as a fluid in the condensed phase, and it starts controlling the surface temperature. And then eventually the water's going to go supercritical. And then maybe that's when it starts falling down at the end, but I don't have a good explanation. So it's one of these things that really people can think about. So let's stop there, and we'll pick this up tomorrow. Tomorrow I'm going to basically spend most of the time going through metal combustion and looking at large metal particles and the effect of going to nanoparticles.